After learning these sigma formulas and using some of the other properties that we have learned about sigmas, let's try to use it to find the exact value of this definite integral. The geometric meaning of this definite integral is you have the graph of y equals x squared, and the interval 0 to 1 is from here to there, and you're looking at the area under this curve. Now, because this height is 1, and the triangle with height 1 and base 1 would have size 1/2, the value of this area should be less than 1/2 and a little bigger than 0. So that's something to keep in mind. But at this point, you probably haven't seen any geometric formula to get an area of a paraboloid, parabola like this one. Okay? Alright, so how do we approach this? Well, we start with the Riemann sum. And to give you a better idea, let's make it a bigger picture. So here's 1. And what you want to do is you want to divide this interval from 0 to 1 into equal distance intervals. And then for each of these intervals, we're thinking of these intervals as like building sites for building tall buildings. And we're going to build these rectangles so that the top right corner touches the graph. And that means that we're trying to use the right sum. There are several different methods that you can use for Riemann sum. You can have upper sum, lower sum, left sum, right sum, trapezoidal, or some other ones as well. But we'll just stick to the right sum. And it doesn't matter which method you use, as long as you increase the number of intervals to infinity, which means that these interval sizes will become very, very thin. The rectangle areas that you add up will be very close to the actual area. So we're trying to use the limit of that Riemann sum as the number of intervals goes to infinity to find the actual area. Okay. Now, for any Riemann sum, you should always start by calculating delta x, whose formula is b minus a over n. And our b is 1, a is 0. So that's going to be 1 over n. Then you have to find all these endpoints. Our convention is that always the very first endpoint, starting from left, it will be called x0. The next one is x1, x2, and so far. Now, to get these points, you want to do calculations that's like walking in a park. That's what I said before. And the x0 is always the left endpoint. It's from a to b, so a is the left endpoint, and in our case, a is 0. And then x1, you're taking step sizes, and every step size is delta x, right? So you start from a and you move one step to the right, which in our case will be a is 0, and you have 1 over n as our step size. x2 would be you take 2 steps. So we do 2 times delta x. In our case, we 0 plus twice of 1 over n, which is 2 over n. Keep going, and you see that there's a pattern here. If you have a plus k steps later, it will be a plus k times delta x. So in our case, it will be 0 plus k over n. And eventually, when you go all the way down, you're going to arrive at x of n. Okay, and then that will be like replacing this k by n, which is n over n. So x of n will eventually be just 1, which will be b in our case. So whenever you do these calculations, make sure that xn you arrive at the other end. So think of this as like walking in a park where you enter through gate A and you leave through gate B. Every step size is delta x, and that's how you get to the other side. Alright, so once you get these delta x's and x0 through xn, the next step to do is to figure out what the height of these rectangles are. Now remember, if you know the x coordinate of something, then let's say this is m, then you plug in this m into the function to find the y coordinate, right? And for our case, f of x is x squared. That's our function, okay? And because for any interval, let's think about the kth interval. So maybe this is a better way to do it. So if you have the kth interval, and I'm going to denote rk as the area of the kth rectangle that you construct, okay? And so this is R1, this will be R2, this area will be R2, this will be R3, and so on and so on. And if you look at the pattern here, R3 has x3 as the right endpoint and x2 as the left endpoint. So it's always the case that this k matches with this number, and this will be one less. So RK will have xk as the right side and xk minus 1 as the left side. Okay. Now, because you're going to find the y, the height, by plugging this into the function, what's going to happen is that your height would be function evaluated at xk, and therefore the area rk will be calculated as base times height, because it's a rectangle. So base length is delta x, it's always delta x, all these are delta x, times f of xk. And that's what we will be computing for this specific case. So in our specific case, here's what we found. Rk is delta x, which is 1 over n. And then f of xk, well, our f of x is x squared. And our xk is k over n. So what we're going to do is we'll be plugging in k over n, which is xk, into this x squared function. So you're going to get x squared. And we can simplify this further as k squared over n cubed. Because it's n squared times n, so it's n cubed. Okay. Now, what do? Well, we add up these rectangle areas, and that will be our approximate area. It will be slightly overestimating because we have extra parts here, right? So the area that we want, which is this area right here, will be approximately sum of these areas, R1 plus R2 plus so on and so on, all the way up to Rn. And if I write it out, it'll be like 1 squared over n cubed plus 2 squared over n cubed, all the way up till n squared over n cubed. Now, it's better to write this in the shorthand using the sigma notation. Some of you are afraid of the sigma notation, but it's not that hard. Just think about what changes gradually. It goes 1, 2, 3, 4. That should be our k. And it goes from 1 until n, so you put 1 through n. And then you have k squared over n cubed. Okay? The denominator doesn't change. Or we can just say, oh, we're adding these things, which is this one. We're adding this with k from 1 through n. That's all we are doing. Okay? However, writing it explicitly in longhand actually has its benefits, because you see that 1 over n cubed is a common factor, which means you can actually factor that out. And I want to do this because if you write it like this is actually exactly the same thing as this one. I use letter k instead of I, but this is just a variable to keep track of the changing numbers, right? So whether you use k or I, it doesn't matter. The result is still this one. So what you get is that this must be 1 over n cubed times n plus 1, 2n plus 1, over 6. All right, so that's our area. Now let's simplify that. So 1 of the n and this n will cancel. So you just have n squared. So you're going to get 6n squared in the denominator. Whereas after canceling this out, you can FOIL this out. N times 2n will be 2n squared. You have n times 1 and 2n times 1. Adding the 2n and n, you get 3n. And then 1 times 1 will give you plus 1. Okay. So that is going to be our area with n number of rectangles. But that's just an approximate. How do you make this into an actual value of this area? Well, you do it by, as I said, you want to increase the number of intervals you have. So what you do is you take you say the actual area is now the limit of n going to infinity of 2n squared plus 3n plus 1 over 6n squared. And then you can calculate this by dividing top and bottom by n squared. Let's do that. So 2n squared is divided by n squared. 3n is divided by n squared. 1 is divided by n squared. And 6n squared is divided by n squared. They cancel. This one cancels. This is 3 over n. So you get limit n going to infinity. You get 2 plus 3 over n plus 1 over n squared over 6. Okay? And then 3 divided by n as n goes to infinity would be 0. 1 divided by n squared as n going to infinity will be 0 as well. So you're going to get 2 over 6, which reduces to 1/3. Now, earlier I said that this area should be less than 1/2, right? So it's kind of interesting that like 1/3 would be the simplest number you can think of, the simplest fraction you can think of between 0 and 1/2, and this is has the area of 1/3. Okay. So that's how you do this.